structures, but I would say that the key player in my mind to make precise the geometric structure so that we can really do something was Riemann. And Riemann's fundamental works were in the mid, so hi Sasha, everything okay now? His fundamental work started, well, let's just write here, mid 1800s. So you may laugh, but for me this is not very long ago. When you think of this huge development of everything, for me this is not very long ago. For example, my father's father was alive at the time, at this time. My father's father, maybe almost, yes, my father's father was alive more or less at this time. So it's not very long ago. Yeah. My father was born in 1912. It's about right. There's a marking thing in the United States, the so-called Civil War between the North and the United States and the South. And that's about the time of the United States Civil War. So that's not very long ago, and so Euclid was a very, very long time ago, and so this is really, from my point of view, the beginning, and I will try to explain this. This is what I promised to you. I will try to explain this later on in the course. Right now, it's almost a philosophy. Symmetry is the study of group actions which preserve some sort of mathematically defined structure. I think it's reasonable. Okay. So, the group acting on G will certainly be contained in the bijective, let me write this, the biject X, which is the bijective mass of X. I mean, this is just a formal stupidity. It's completely clear in this situation that that's what I mean. Nevertheless, you should keep that in the back of your mind. Okay. And now our examples are very interesting. We're based on starting with the square. S, and which is contained in the Euclidean plane. And it led us to consider various things. This led us to consider, you see, it led us to consider various important things. I will write them now in small generality. The n-dimensional affine space modeled on the vector space. Now I'm going to dimension n. I think dimension 2 is, of course, the plane is very interesting, but I think higher dimensions are also very interesting, and in my mind more interesting. The plane is a special case. Yes? I always tell when I give applied lectures on this subject, if you look at the numerical analysis problem of the stress of the forces, understanding the forces on an airplane wing, I'm not talking about a Boeing 737 MAX. I'm talking about where the problems were not on the forces on the wing, it's something else. I'm talking about classically a problem I know about, the Boeing 747. It's a classical airplane. The forces where of having this big wing attached to the airplane here, you have to understand the forces at something like 17,000 points. And to understand those forces, yes, you have to solve equations and do equations with symmetry, in fact, in 17,000 dimensions. Yes? In physics, we can discuss it a little bit. First, you do in 3 dimensions, then certainly 4. And now I know about 26 dimensions. What other dimensions do you favor in physics? And do you have a favorite physics dimension?
I like 4.
4, just 4. You're 4, okay. So we're thinking about perhaps space-time. Yeah. But you see, what happens is you have maybe space-time, but at each point in space-time you have a big structure. Yes? You have 4, and then at space-time you have a big structure lying over that adds a huge dimension. Yeah? You never thought about this, but if you've not thought about this before, I think it's a little important point for me to make. If you are considering what we call in celestial mechanics, so Himmelmechanik auf Deutsch, celestial mechanics, you're interested in the motion of particles in time. So that might be your favorite thing. Time, it might be 4 dimensions, right? But each particle is going to get 4 dimensions. So your phase space, your huge space, maybe is, when you're considering all these particles together and so on, may be very high dimensional. Right? It may only be 4, but you may be you can imagine. So high dimensional mathematics is, in my mind, the mathematics. So I took this example here, the square dimension 2, but I'm really interested in higher dimensions. And if you're interested in higher dimensions, then you're certainly interested in the affine group, affine space modeled on Rn. I hope you understand what that is. That is a set with the free transitive action of Rn. Right? You have the translations here. And we have studied this group on this, the symmetry group, G, on this, the symmetry group. We give it a name. If you're a good mathematician, you give it a name that reflects it a little bit. It's the affine group over the real numbers. That is the symmetry group of this thing. And we know that this thing is a semi-direct product of the linear part. Once you've chosen crystal as the base point, I'm sorry, I'm doing it again, then you apply translations, and you can fix that base point, and then you discuss linear transformations. So we have this group. Now we learned a tremendous amount. I'm reviewing the way you should review as students mathematical work or physical work or computer science work. It doesn't matter. What we've done before is that, and we've pushed it a little bit general so that we have the affine group in dimension n and so on. It's this is translations, acting as translations, and acting as linear transformation. Yeah. And the key is we know how conjugation. So the key fact, and I talked to you about this semi-direct product business, is that we have elements here which are linear transformations and translations, and the key is that how linear transformations act on translations. So linear transformations T act on translations small t by T of small t is conjugation. Yes? And this is, depending how you set it up, this is just the linear transformation applied to the translation, or it depends on, maybe you have to look at your notation. Maybe it's the linear transformation inverse applied. Yeah, I'm not sure, I'm never sure what this is. So this is what conjugation does. In my lecture yesterday, I called this T hat. The conjugation of a translation with a linear transformation is another linear translation, is another translation, and this translation is just T of that thing. So if you have a conjugation, you have a good semi-direct product. In general, you don't have a semi-direct product, but here you do. So starting with this definition, and starting with the first example that comes to your head, the square, right? You're forced to discuss the plane. We haven't even gotten to it here, but we've gotten very close to it with the affine space, and we got to a very interesting group, the affine group, and here it is. It's acting as translations and linear transformations. If you fix a base point, you see very easily the linear transformation. And so since it's a product, you better, a semi-direct product, you better tell me how this thing conjugates that thing, and I just told you. Okay. All right? Then we realize that we need to understand the E2R, which is the group of Euclidean transformations of the plane. Group of Euclidean transformations. Transformation acts as the group. So maybe I should write here, acts as the group of Euclidean transformations of the plane. And you say, well, Professor, look, we don't need to stay in dimension 2 all the time. Let's go to higher dimensions because it has nothing to do with dimension 2. Yes?
So that if you conjugate the translation with the linear transformation, it was in dimension 2, it was kind of clear that this still gives a translation. Why is this clear in n dimensions?
Oh, okay. That's very good. I mean, yes? So I think I'm going to write your question. So let's take a detour to answer his question, but then we'll go back to, it's the same question for Euclidean or anything else, right? So we might as well answer it for that. Mr. Weiss's question is, let's see here, is why is it clear that, I'm going to write it in my language, which I like a little bit better. Why is it clear that, let's see, now why is it clear? Why is the action of conjugation by GLN in higher dimensions, GLNR, on translations, let's call it Rn plus. That's your question. Why is the action of GLNR by conjugation on, why is the action of conjugation by GLNR on the translations given by T inverse equals T of T. I even have to explain what that notation means. It looks so, you're shaking your head.
I mean, T of T, I mean, we define T of T as the conjugation.
No. So that, I was a provocation what I wrote here. I could do that, and then I wouldn't have answered your question. I would have to define T of T.
Yeah.
But let me go to the next board and look at this. And then I think everything, you understand, everybody understands what he's asking about, right? It's completely clear. I think in this notation it's completely clear. So let's just see T of T. So the translation, let's write something down. So the translation of a vector is equal to V, let's write it V plus W. If you like, I could put a little W here to remind you it's the translation by W, but I'm not, it's too much notation, right? So I'm going to write it, T of T inverse of V equals T of T inverse of V equals, maybe I'll write all the brackets here to really bore you. It doesn't matter, it's associative. So, right? So this is T of the translation of T inverse, that's T inverse V plus W. This is equal to, I do it term-wise because it's linear. This is equal to V, win, T of W. Right. So it was clear to me, but because probably all my life, I've done this calculation 100 times in my life. And so I've asked Mr. Wise's question many times to myself. But the only answer to the question is do the calculation in some sense.
Yeah.
In some sense. But also intuitively you should say, well, you have a translation, linearity should preserve translations in some sense because just what we're dealing with here. But then you have to write it down. I think then the physics is right and you have to check it out. Right? So I think you do have to do this calculation. Right? Okay? So that's the reason I wrote it in this most, but that in fact is what I wrote is correct. Yeah, so thank you very much for this question. So let's put this here up above. And so let's put here T of V equals V plus W, and then that implies this. Okay, so that's a wonderful thing, and we have, yes?
I have a question. So here we are assuming that the structure that we need to preserve in the special case E2 is the same structure that we need to preserve in n dimension?
Yes, is the affine structure. Yeah? So I talked about that a little bit. I talked about dimension 2. Let's talk about his question. He says, what do you mean the structure needs to be preserved in dimension n in the affine space? Is that the same as in dimension 2 in the affine space? And in affine space dimension 2, you only need to preserve lines, affine lines. But in affine dimension n, you need to preserve lines, planes, and everything else. And not only that, you need to preserve the equivalence relation. If a line is contained in a plane, then when you map it, the map line is contained in the map plane.
That's what I mean. So
that's what he meant. And the answer is yes. But as you see, it's only reasonable to ask the question, what are those transformations? And that is the fundamental theorem of projective geometry, what I mentioned the other day. So your question is the fundamental theorem of projective geometry true? Okay? Very good. Yeah. So I can't tell you now why it's projective geometry, but it will become clear to you.
So we meant to write small t there.
I probably have small, oh, yeah. So, thanks. I don't do that on purpose, but it's very educational for people to watch my stupid notation mistakes. Right? It's sometimes confusing, right? Okay, so that's great. So we understand that, and the group of Euclidean transformations. So let's go back after Mr. Weiss's question. So En, the transformations in En, transformations in En should preserve the standard Euclidean structure, and I'm going to write that as the standard inner product. The standard coordinates is VW. It's the standard. I'm answering the question you asked about higher dimensional affine space. I'm answering now about higher dimensional Euclidean space. It's just V1, W1 plus and so on. I'm just talking about the standard thing right now in standard basis, and I'm not making a big deal out of this, just standard generalization. And you can see here that if you have a vector which is related, has coordinates x1 through xn, as a column vector, so let's write it as a column vector like this. That if you have it in standard coordinates like that, then the length of this thing squared, I told you always to write a square. In the standard, maybe I'll even write standard here. Let's write standard. In the standard inner product is just exactly what you want it to be. The standard norm. So you get the standard geometry. Believe me. And you look at this group for a while, and translations preserve it, so it's only the question of what the Euclidean group is in the linear part after we fix the base point. And that by definition is some group which we call the orthogonal group. Those are the linear transformations which preserve this thing. So these are the linear transformations which preserve the this inner product, standard one. The orthogonal group, semi-direct problem, they're the subgroup of GLNR, semi-direct problem, the product with the translation. You see, if you go home and tell your mother some horrible thing like this, she will think you're it's terrible, right? But you understand what it is. It's just translations and linear transformations which preserve the inner structure. And every element here, if you like, is a pair which derives a linear transformation and translation, but a special one here. And we write this multiplicatively as a transformation. Yeah?
San, not two, right?
Huh?
San, not two. En.
Oh, yeah, thank you, yeah. Not to E-N, you're right. I wanted to make a little jump to E-N, yeah, but more or less clear as what it said. And for n equal 2, we know that in the standard basis, that a transformation T has a matrix of T equals, and now I'm going to lie to you a little bit, cosine theta, sine theta. I did this yesterday. This is of course because it's the column vector E1 goes to a column vector which has a squared plus b squared. It has to have length 1, so a squared plus b squared is 1, so cosine theta, sine theta, minus sine theta, cosine theta. E2 goes to that thing, but maybe not, or, you see, of course, this is a rotation of a vector. If you apply this matrix, it's a rotation through an angle theta. Here's t of theta, and if this vector corresponds to the vector, I don't know, column vector x1, x2, then this thing corresponds to the column vector cosine theta, sine theta, minus sine theta, cosine theta, x1, x2. So the action is by matrix multiplication, of course. And that's that positively oriented thing. So this really is only positive oriented. So it's either this form or the other way around. Or, I'll write it one time, the matrix. So that's the matrix of T. T is the same thing. So I'll write it here. But before doing this, you screw it up by reversing the orientation. Right? You reverse the orientation and then rotate. Right? So those are the two possibilities. Either you don't rotate or you do. Either you rotate or you do. And either you reverse the orientation or don't, and then you rotate. That's a very simple matter in dimension 2. Yeah? And you can check, it's a very easy calculation, you should check. But it's a good calculation for you to check. In higher dimensions, we're just talking about here. En, if you have a transformation in On, I mean, translations are completely clear in higher dimension. It's only a question of what this is, yeah? And it preserves the structure. That means it preserves the structure, and the structure is the inner product, and the structure needs to be preserved by this guy. And so that means if you apply the guy, you don't change the structure. That's the first line of my definition up there, right? You apply the guy and you don't change the structure. The structure remains invariant. So that's exactly the thing. And if you wish by just then you would say, well, let's do it by this thing is, I mean, it's all right to do by brute force. This thing is, you take the transpose of this vector, it was a column vector, you make it a row vector. Just for fun, I'll write it as V1 through Vn as a row vector times W1 as a column vector and so on. All right, that's what that guy is. And then this is a statement that, let's write it out, that V transpose W equals T of V transpose T of W, and transpose reverses the transformation around. So this is phi T transpose T of W. So in fact, all you have is ONR. You see, if I ask some mathematician, they'll just say, well, ONR, these two things have to be the same, so you just check, these are the transformations in GLNR, the linear transformation, so that T transpose T equals the identity. You're not allowed to do anything here because that says this stays the same. This is TW, right? So this better be the identity. You can check that that's right. And then here's an equation. So you should learn, what you should learn is a stupid thing, but I know you well enough to know because you're beginners. I know you will not do this stupidly. You would say, here is a stupid remark, but very important. Stupid, important remark. It's a stupid important remark that T times T transpose T equals the identity is an equation. Is it not an equation? Right? There is an equal sign. Right? This is an equation. Is it not? T transpose T equals the identity is an equation. The proof is there's an equal sign in it. Right? And then, if you're not so stupid, you say, where is that an equation? An equation is on some sort of set. Right? What this really means is ON is the set of T. This is a horrible place, GLNR, but let's say in the linear maps, so the linear maps are called endomorphisms of R. These are all n by n matrices, are all matrices. All matrices. They don't have to be invertible. This is just all matrices. We call this the endomorphisms of R. The linear endomorphisms of R. The bijective linear mappings, such that T transpose T equals the identity. Yeah. That's an equation in this endomorphism place, right? The space of all matrices. Tell me something about the space of all matrices. What's it look like? Space of all n by n matrices. What's it look? Go to the board, Mr. Pham, and draw a 3 by 3 matrix for me. 3 by 3. Have some courage, man. Come on. Just draw a 3 by 3 matrix. It's completely a general one that you would look at, maybe 3 by 3. Right. I said these are all matrices of dimension n. So take an example of 3 by 3. Don't make a square. That quite often make it round. Because square sometimes means determinate, right, or something. Well, Mr. Pham writes the identity matrix now. Mr. Pham, right, that's okay, that's the first time. Mr. Pham is not stupid, but he wrote a stupid example. So, what is the most general looking matrix of that type? General, this is too special. What's the most general looking matrix? That's A11, that's looking pretty good. Yeah, that's A12, A13, very good, he writes beautifully. Good, that's wonderful. Great. And now I'm tired of you. No, stay here a minute. This is 2 minutes, because if you do this in 4 by 4, you're going to get very tired writing, yeah? So how would you like to write it here? Great. Well, maybe you better tell me what I and J are doing. You're not Einstein. Okay, I equals 1, 2, 3. J equals 1, 2, 3. Good. Well, but I'm even a little bit better than you. I and J are running between 1 and 3. Yeah, isn't that a little bit simpler to write it like that? Yeah. So, Mr. Pham, tell me what let's in short. What does a completely general matrix look like in dimension n? You wrote it in dimension 3. I don't think. Oh yeah. Okay. Yeah. Very good. Very good. Thank you. Yes, good. How much freedom do you have here? Do you know what I mean? How many directions do you really, how big? N squared, sit down. Okay, the space of endomorphisms, you prove a theorem. The space is very good. The space of endomorphisms, all matrices, over R, or over anything. You didn't tell me what that was doing. That could be a complex number, a real number, a fancy number. Yeah? The space of n times n matrices is equal to the endomorphism space is in a very natural way, if you, I have to write endomorphisms here. Endomorphisms of R and of R. Or maybe I should write endomorphisms of Rn. That's maybe a better way to write it. Is in a very natural way equal, and you'll have to say what natural means, but it's Mr. Pham's theorem, to Rn squared, right? Isn't that what you said here? Right? Because he said everything here, you don't care what it is, so it's Rn squared. Right?
Does orthogonality imply invertibility?
Very good. That sounds like a music line. Does orthogonality imply? So these are just the endomorphisms. And it's a good question he's asking, right? You see what I did? And then I had this following picture in my mind. Here are all the endomorphisms. And here is the identity, and here is this is interesting. Here are the endomorphisms which satisfy the equation T transpose T equals the identity, right? You're asking exactly, is that really an interesting equation, right? And I say to you, it's really a very heavy equation. It's a very big equation, and you can check it, okay? So let me tell you the answer, but I think it's good for everybody to check it for fun. It looks like a very heavy equation when you think about it, right? So, it's an equation in matrices. So that means, as equation in numbers, it's n squared equations. So that's it, right? Because it's an equation of matrices, equation in numbers, that means it's n squared different equations. So it's a huge number of equations, right? And so then you work a little bit. It's not too bad, because you gain some knowledge in dimension 2, and that's the reason it's always good to look in low dimensions, or in dimension 3. Usually dimension 2 is a little bit special. I would recommend maybe fooling around in dimension 2, but I would go to dimension 3 rather quickly. And I would not write A, I would write X to remind you it could sort of vary as anything, right? So, the little proposition that you will prove easily is the matrix that T is in an orthogonal group, O and R, and that means if and only if the matrix of T, so that's really what we're talking about, and I'll emphasize this is the matrix of T in the standard basis, which is itself an orthonormal basis. Remember, the standard basis here is E1, E2, E3, E4, E5, all the way up to En, and that is really an orthonormal basis. They're all orthogonal to each other, right? So that means that this matrix has to take each one, T of E1 and T of E2 and so on. So we have the matrix of T. So you have to see, where does E1 go? Where does all the E1 go? And then there's, where does all the E2 go? I don't have any idea. And now it goes like this, right? That's the way you keep in mind where it goes. And this column vector is T of E1. And this column vector here is T of E2, right? Matrix was a wonderful creation for as an aid to understanding some stuff. E1 is orthogonal to E2 and so on and so on and so on. So these things have to be orthogonal to each other. This means this matrix here, T of E1, T of En, that's a matrix now, N by N matrix, is an orthogonal, is an orthogonal matrix. Matrix in the sense that T of Ei, T of Ej is equal to delta Ij. Delta Ij, you're familiar with that notation. It's equal to 1 when I equals j, and is equal to 0 when I is, right? So if this thing is an orthogonal transformation, then it preserves the form, then this matrix is orthogonal, and then you can check other way around. If the matrix is orthogonal, then it really satisfies this equation. So the orthogonal group is, I'll write it another way, ONR is the set of T such that the matrix of T, so T of E1 through T of En, this is the matrix of T, is orthonormal. Orthonormal. That's still a wicked equation. You can imagine how many, right? I mean, there's many equations. So it's a pretty bad thing. What you should notice if you're interested in mathematics, these equations are quadratic. Is it not true? Because, right, an individual equation, this thing, T of Ei, T of Gj equals delta Ij, is a quadratic equation. So you have a huge number of quadratic equations, right? And so you should think what this is looking about. Here is one quadratic equation. So equation 1 It's nonlinear. It's a nonlinear condition. This is equation one. A professional mathematician says, look at those things. They are nonlinear equations. It's not some stupid linear thing. Yeah, these are curved equations, quadratic equations, like spheres, right? These are quadratic equations. This is maybe equation one. This is equation two. Maybe it looks like this. And then an equation, and here's where both equations are satisfied, and so on and so on and so on. This is the intersection of a bunch of quadratic hypersurfaces. Pretty interesting. And actually, it's very interesting, the geometry of all these equations, how this orthogonal group looks. And so the end result was, again, I'll write it again, the Euclidean group in general, with the standard inner product, is the orthogonal group semi-direct product. It's the same discussion as before with the group of translations. And these are the proper, the correct transformations of this. Not after 3 and a little bit more, 3.5 lectures, right? You've gotten to some serious mathematics, right? Yes, sir.
Maybe it's just a notation, but so the endomorphisms are also invertible, or
No.
So they're not invertible. So
0 is an endomorphism. It's a linear map.
okay, so it's just all linear mappings.
Yes, I thought I said that, didn't I?
Yeah, okay, but then I still didn't understand why those are necessary, or why the orthogonality implies invertibility. I mean, this.
Okay. Okay. No, I didn't answer your question. It's so implicit in my brain that I forgot to answer your question. So again, I didn't answer his question, but let me answer it now. But I did say, no, your first question was, does, I don't know, is orthogonality a special condition or not? Yeah, that's one way of asking. So I'm saying, I showed you all the equations for orthogonality, right? And one way of answering your question is that that matrix, if you see those column vectors, they form an orthonormal basis of the set. Is that not true? T of E1, T of E2, T of E3 forms an orthonormal basis of Rn.
Okay.
Well, if it's a basis, they're independent.
Right.
And they're independent if and only if that matrix is invertible. I don't know if that's a non-trivial remark or not. I think it's a trivial remark. And I also think that it's a trivial remark if you take something that preserves the inner product and it has a kernel, then T of V is equal to 0, right? That means the inner product of V with anything else in the world is 0. So take something where V in inner product of that guy is not 0, and it's impossible that T preserves that inner product. So that's an argument that T of V can never be 0 unless V is 0. And that's the statement that the linear transformation is invertible. But all of these statements are pretty fast for people. You will have good linear algebra coming up next semester. You've had a little bit of linear algebra by now, right? So it's a quandary a little bit. You have a little bit of linear algebra. But what we're using here to answer Mr. Weiss's question is an operator endomorphism is invertible if and only if the only way you can get 0 is when T of V is equal to 0 if and only if V is 0. Right? Because otherwise a lot of invertible means 1 to 1 and so on bijective. Otherwise a lot of stuff goes to 0. Right? You can only have 0 going to 0. Right? Otherwise it can't be invertible. Okay? So keep that in mind. And this is strong motivation for you to do good linear algebra next semester, in some sense, right? Really think about these little things like this when you're thinking next semester. Okay. I didn't think about this that way, but I think it's good. Okay. Okay. Okay, so let me just write here on the board what we have. We have AN, and we have NR, and we know what that is. It's GLNR. I'm just repeating so we have some organization here. This works out with semi-direct product business. We have the Euclidean group, ENR. That's the orthogonal group, semi-direct product, Rn plus. And now, and we talked about this orthogonal group, and we learned the orthogonal group is defined by an equation T transpose, by the equation T in GLNR, such that T transpose T equals identity. We can answer Mr. Weiss's question here also, because if T of something was 0, then you would have 0 equals the identity applied to that thing. That's a contradiction. Okay, but again, it's using this thing about if it's invertible, that means that it's nothing goes up onto 0 except for 0 itself. Right? You can see how powerful that statement is. Right? Kernel of the operator's truth. Okay. Okay, that's that. And now we learned we have what about this matrix? What's going on here? What's going on here? Remember, we had this matrix, this reflection matrix, right? Right? Where the devil is it here? What could be a reflection matrix here? This thing, E1 goes to E2, and E2 goes to E1. That means that this picture, E1, E2, when you're talking about that as an oriented, well, I have to do this way, right? When you think of this is E1 and this is E2, compare this picture to this picture, E2, E1, and you ask yourself the question, a really good question, by the way, discussed in detail by Kant in the old days when he was trying to understand, he became a philosopher in the classical sense, but when he was younger he was interested in precise mathematics. E1, E2, compare this E2, E1. Can you take E1, E2 and move it around in a reasonable way with no flips or anything? Move it around continuously, move it around continuously. And can you do that? Can you move it around continuously and come over with E2, E1? Do you get what I'm saying? Can you start with E1, E2 and move it around continuously and get E2, E1? You believe it, you don't believe it, right? You cannot do it. Okay? You cannot do it. You cannot do it. Okay? You want me to tell you why? Here's why. I'm going to draw you a picture of continuous movement might be in GL2R. Right? Continuous linear movement around, right? So, in other words, this frame, E1, E2, goes to this frame by a transformation, E1, T of E1, T of E2. Okay, and suppose we move it around, 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 move it around. So, and then at the end we get E2, E1. That means T of E1 equals E2. This is a big trend. No, this is not T. This is all this movement. Let's call that movement M for movement. You move it around. T of E1 equals E2, and you move E2 around, and you get E1. Right? You move E1 around, you get E2. You move E2 around, you get E1. What's the determinant of M? Well, what is the matrix of M? M of E1 is E2, right? M of E2 is E1, right? What's the matrix of M? -1, right? I really just wrote down the transformation we've been talking about. It's -1. Okay. Right? And now, because you haven't looked yet, here is the endomorphisms. Here's all endomorphisms. Let's say the endomorphisms of R2. Here's the identity. And I'm going to make a mistake. Identity. Let me write this as identity. I'll just call it identity. This is going to be the identity. And this is going to be the picture of, oh, this is a horrible picture. If I take any matrix and move it a little bit, and if the original matrix was invertible, what about the moved matrix? It's invertible, right? You believe me? How do you prove it? Yeah, come on. She nods her head, she'll go, I'm going to put you on the spot. I take a matrix, yes? He's a matrix. Call me matrix. I'm a matrix. So, I'm the matrix, not you. Now you grab a hold of me, here, grab a hold of me, and move me. Okay, and maybe that moved the first column a little bit, or something like this, right? And now Crystal grab a hold of me and move me a little bit. I'm really happy to have Crystal move me. Oh, thank you. Oh, it's wonderful. So, okay, these two young people move me a little bit as a matrix. Yeah?
I mean, to show that it's open open set, we can just say it's a complement of the preimage of 0 of the determinant.
Very good. So a matrix is invertible, as you know, and as a non-trivial remark, if and only if its determinant is not 0. Right? And determinant is equal to 0 is an algebraic equation. So the correct picture here is not this picture. We have the 0 matrix, which is not invertible, and you have all of the matrices which go through 0, and that's the non-invertible matrices. So let me call it the determinant. This is an equation. The determinant of the matrix of T equals 0. Right? That's an equation. It's a horrible equation, by the way. Right? I mean, you can have fun with this equation. Anybody can write A, B, C, D down, and then you have the determinant of A, B, C down, and that's A, D minus B, C, right? And then you're going to have fun writing down a determinant in higher dimensions. You know how to write it down in dimension 3. And you do this, you go wham, 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 and wham, wham, right? Isn't that what you did in school? You do that in dimension 4, and you're going to start getting really mixed up, and so you really want to know what the determinant should be, and then you learn about it, and it is an equation. It is, you know what it is geometrically? What is it? Who's speaking? Did you speak?
Yes.
What is it?
I said volume.
Well, that's the volume of what?
Oriented volume.
So oriented volume of what?
All of the vectors that are there.
Okay. He's very shy. You take the column vectors and determine. They determine in a wonderful word in English is called a parallel pipette. In German it's a much easier word, it's called a Spat, S-P-A-T. So it's easier to say, parallel pipette. It's very hard for me to say, and I don't know how it's spelled. But you take this thing, and that's, in dimension 3 you can see it. I mean, it's defined, dimension 3 you can see it, but in higher dimensions it's what it is. And the determinant is the oriented volume of that thing, okay? And you notice that the determinant can be negative or positive, right? Right? And so this is where the determinant is, and this is where the determinant is positive, and this is where the determinant is negative. Okay? Right? Yeah? Now I want to ask you a question. If you have one of these parallel pipets here, or one of these things here, or a matrix of an orthogonal transformation here, and a matrix of it there, and you go to there by a continuous curve, what do you have? What happens? Well, what happens? The determinant is moving. It's moving, it's moving, it's moving. Oh, on one side it's negative, on one side, on the other side is positive. There's a function that you learn from Mr. Kevin Malahai Karai, my good friend. If it's negative on one side and positive on the other side, it has to pass through zero because it's continuous, right? That's called the intermediate value theorem, is it not? That's great, everybody knows, really knows that theorem, that's right. So by the intermediate value theorem, you can never go continuously from one orientation to the other, because the orientation is measured by the sign of the determinant. So we have to worry about the sign of the determinant. And that's the reason in my lecture I wrote on the blackboard two different signs, because one will be the orthogonal transformations with positive determinant, and the other will be the orthogonal transformations with negative determinant. And we will see that then that group composes into the semi-direct product of that group. Okay. So let's write O n plus R as equal to set of T in O n R such that the determinant is positive, and the set a set of O n R is all orthogonal transformation. Okay? And you easily see that O n plus R is a normal subgroup of O n R. And it's very interesting to think about what is the difference between O n plus R, the orientation preserving transformations, and all of them. Just to convince you that there are some here that aren't there, right? You have some easy ones, right? Here's one. A lot of easy ones, right? Isn't that an example of an easy one? Right? Yeah? Well, that's good. That's a reflection that has order 2. Oh, no, the determinant, what's the determinant? Oh, the determinant is 1. Okay, right? Minus 1 times minus 1 is 1 and 1. Oh, I screwed it up. Minus 1. Right? Yeah, I think that might be really the interesting guy. That might be the interesting guy. Yeah. That might be the interesting guy. Think about it. That may be some generalized reflection. Let's call this thing R. And the question is that about all? Almost, is that essentially all we need to understand? Essentially everything? All? What that means is that let's let R generate a group of order 2, which is a reflection group, C2, and I'm asking, is the full orthogonal group just the orientation preserving orthogonal transformations with a determinant +1, semi-direct product with this group of order 2. Is that everything? You see what I'm saying? You certainly got to have this element. That's orthogonal. I mean, minus 1, right? But maybe you need more. You understand what I mean? Maybe there's some other. I don't see any more. Do you see any more? Oh, I see another one. I see another one. All right. All right. And now the question is, maybe you can get from this one to that one in some way, right? So maybe somehow or another these things are, you only need one because you can get from this one to that one in some way. Maybe. Maybe not. Yeah? You should try. Okay. So, let me tell you that this is quite often the problem in physics, that there are these spin groups. Spin groups, are, as you know, are related to the coverings of the orthogonal group. And a lot of these spin groups in physics are not connected. We're talking here about connected components. The various components will be given to you by these various elements of these exterior finite groups. And you need to really understand, is that all? Are there anything? Any more? That's all that's going on. So if you haven't done that calculation, do it. Okay? It's a very useful calculation. This is how spin appears with several components. This is how pin occurs with several. Okay? Okay. And then finally, you see that was almost just a review. Finally, the symmetry group, as we've seen, of the square is the stabilizer in the Euclidean group, which we now know what it is, of the square. And we saw yesterday that this is the dihedral group with 8 elements, which is the semi-direct product of the rotation piece with the reflection piece. I hope you know in 4 lectures that's a serious statement. Right? That's a serious statement about what is the symmetry group of the square. And in order to do that, you have to go through, really understand this amount of mathematics that I presented to you. I think you basically do, but you have to look at the notes which I will give you, and do your own exercises. And if you get interested in something here, ask me about it, and you can write a little paper for the courses. The only requirement for this course is to write a little paper. And you were asking, some people audit in this course. Even if you're auditing the course, it's a good experience to write the paper, and I'll look at it and tell you and criticize it. It's a good experience. It's a good experience. Some people are here who were in my recent course. You several. I think it was a good experience to write these papers, right? You don't think so? Your paper was actually good. Not that I'm surprised. Okay. Okay. So I think we had a good time doing that. Oh, excuse me. All right. Now, we're almost reviewed with everything. Well, I want to underline something that we've been implicitly talking about. So here's something that seems simple, but group actions, the simplicity in what we've been talking about, group actions on groups. Group actions on groups. This is of fundamental importance, and you will not believe how modern this subject is. The first time I've seen this explicitly in the literature is in the 20th century. It's unbelievable. Okay, so G is a group. And in this discussion, G is also equal to X. And then we're talking about G actions on X, but X is really the group, but I want to separate the two letters. I mean, X is now the group. Okay? So the first action is X is an element of the group, and G is an element of the group. And I let G of X be G times X. Yes? I hope you're satisfied. That's an action, isn't it? That's a free action. If G of X equals X, then you multiply that off of that, so it's a free action. You check it. It's a free transitive action. Check it. Of course, it's free and it's transitive. Do you see any other actions like this? Anybody? Here's my right hand and here. You see any other possibilities like this?
Consider conjugation.
He makes a huge jump, smart guy making a big jump. Let's go a little bit slower than that.
Oh, right, translation.
What about this one? Right? Now here we go. That's not the same, maybe. If the group is not commutative, it's not the same. So let's go very carefully here in this business. It really makes a difference. We say, in this case, the left action of G on G equals G times G. We say the action of G by left multiplication on G is this action which is defined on the left at G times X. The right action of G on X, on the group X, G is defined by the other way around. That's why I was going my right hand and left hand here. I was being, yeah. Okay? Now, you're going to force me to be a little bit careful. Let's have some fun. Right action of G times H on X. That's equal to X times G times H, such times G times H. That's equal to X times G times H. That's equal to the right action of H applied to the right action of G applied to X. All right? Isn't that true? Let's look if I did it correctly. The right action of GH on X is multiplying on the right by G times H. And I use just the associativity of the multiplication, that's nothing. And that's the same as X times GH times H. That's the right action, multiply on the right by H of the right action of G on X. That says that the right action of GH equals the right multiplication is equal to the right multiplication of HG. Do you agree with me? Right? This is a trivial thing, right? Do you understand my problem here? This is no longer associative in the good sense. The associative root, you see it reverses. The right action of GX is the other way around. It's the opposite, it's anti-associative in some sense. right? It's anti-associative. So this thing is, we call this thing, if it's like this, we call it a left action. And if it's like this, with this thing's good in the terms of left and right, and this one we call a right action. It's good to allow both. In the first definition of an action, you would like to have G of H of X is G of H of X. That's what you would like to have, right? But you won't have it in real life because you have multiplication on the right. Okay. Now, there is a remedy for this. Do you know the English word remedy? If you're sick, you need to take some medicine and fix yourself, and the medicine fixes you, and it's called a remedy. Remedy, right? So you might define a new action, G of X is equal to X times G inverse. You can do that, you're allowed. Right? I'm allowed to do that. And now you will see, because I did that, I turned around this relation. And so this action is now actually a left action. It's a good action in the sense that we like. So if we really want to turn it around, we will, the way to turn things around, turn around with a right, so right action by G inverse, right multiplication by G inverse is a left action. Okay? Everywhere here we've really implicitly talked all this, and then Mr. Weiss he jumped way ahead. Usually, I don't want to be critical because usually you don't, right? I mean, but you jump way ahead to conjugation, which is somehow non-trivial. This is almost trivial, but conjugation is something slightly non-trivial, I think. Yeah. So conjugation action is by the same thing. It's an action of the group on the group where the group is X. And X gets mapped to Gx, G inverse. And we've been using this all along in all of our discussions. What happens with conjugation? This is the conjugation action. And if you like, this is left inverse, left multiplication by G times right multiplication by G inverse of X. And left and right multiplication commute. That's really nice. Right multiplication by G inverse commutes with left multiplication by G. So this is conjugation. Okay? Okay. You've seen that that's appeared. Right. That's appeared everywhere. And now a little bit of a modern viewpoint. If I take a group G, and I think for 10 minutes, and I say, what are the relevant subsets of G? Let's talk about that a little bit. Okay? You're sitting or taking a shower in the morning, and you're thinking about a group, any group. And you say to yourself, well, we talk all the time in mathematics about the subsets of the thing. What are the interesting, relevant subsets of a group? Then you say to yourself, Professor said at the beginning of the course that we're interested in things that have mathematical structure. Right? So subsets that are defined by, not just any subset, but subsets that are defined by mathematical structure. So if you're in a group, what would be the subsets defined? What would be the first subset you would say that you can see that's defined by mathematical structure? If you're inside a group someplace, what would you say? Anybody? And courageous. Start having some courage. Okay, say the empty subset of something stupid, and then get started. It's a group. It's a group. What is the structure? The structure is the group structure, right? What are the relevant subsets?
Each.
The identity component.
Well, there he goes again. You're right, in some sense, that's interesting. That's really, here's the identity component of the group, like GLNR. That's what you have in mind. Then you have another component with the determinant is, yeah. But that is really fancy. I mean, you really impose. I didn't say in GLNR. I give you a group. You're showering in the morning. You're not awake yet, and yeah. And I say to you, what are the interesting subsets of a group a priori with nothing, no other? What? Somebody. Subgroup. You're very modest, quiet guy said subgroups. Isn't it true? Isn't that the interesting subsets of the object, which is, yeah? Okay. So, let S, just for fun, of G be the subgroups of G, the set of subgroups of G. Set of H, subgroup set of G, so that H is a subgroup of G. And we talk about it all the time. You have the affine group, the translation groups, the subgroup, GLNR is a subgroup, the orthogonal groups, the sub. These are the relevant subgroups. Yeah. Okay. Let's look at the associated action of G on subgroups. I.e. on S of G. You understand what I'm saying? You take a subgroup, you apply G to it, you get something, yeah? Okay, we have some choices here. Let's suppose, let's look at this left action. So let's let NH be a subgroup. This is the symbol for a subgroup. That's the symbol, it's a subgroup. That's the subgroup symbol. And let's do left multiplication. G times H. I multiplied H by G, and I got G times H. Is this a subgroup? You believe it? I don't believe it. Do you really believe that's a subgroup? Well, let's check an example. Yeah? You okay with an example? Yeah? Let's see, let's let G equal R plus. R plus. Let's try to make one with R, the simplest thing we know. R plus. And H equal 0. Ha ha, tricked you. Right? H is a subgroup, right? And, okay. And now we have the number 3 in G. And now we take 3 times H, which is multiplication. We're really talking about the additive thing. That's the set consisting of 3. You agree? You add 3 to 0. That's no subgroup at all, right? That's certainly not a subgroup, right? 3 plus 3 is 6, it's not there anymore, right? 0 plus 0 is okay, it's because it's still there, that's a group. But you translate it over, and right? And it's no longer a group, you agree, right? So if this thing is not necessarily, this is not, maybe you're lucky, but this thing is not necessarily a subgroup. Okay? That's interesting, right? So you have the action of G by left multiplication on G. you look immediately to the associated action by left multiplication on the subgroup, it doesn't work. So it doesn't work. What about right multiplication? Take a subgroup and you map it over to this right multiplication. Wow. That's obviously the same discussion. This is not necessarily a subgroup. Right? It's not to be obviously. Okay, any other choices? There's one more choice. Conjugation. Right? Let's see about conjugation. So let's look at this on the whiteboard here. Conjugation, let's check it. So let H be a subgroup. And let's let G be an element of G. And then you take H and you map it over to the conjugate of it. Let's check that, let's hope that that's a subgroup. I tend to believe it, right? Let's check it. If you take two elements of this, Gx, G inverse, multiplied by G, Y, G inverse, I know how to do the multiplication, right? It's wonderful. It's equal to, do you agree with that? So you take the conjugate of one guy, and take the conjugate of the next guy. This is this action. You're moving something over by conjugation, over by another one, and you multiply together. It's wonderful. The conjugate of one guy by G, the same G, times the conjugate of the other guy by the same G, is the conjugate of the product by the same G. That's wonderful, isn't it? That's wonderful. So this implies, if you check it out, that conjugation action of G on the subgroups of G. It's very interesting. It's a geometric exact. So you look at the space of subgroups of G. This is subgroups of G. We were talking about structures all the time. You have a group. You look, what is the good thing associated to it? All the subgroups, right? These are the subgroups of G. And now you have the G action. You have here a subgroup, H, and you push it around with the by conjugation. This is G of H by conjugation. Conjugation of the group G acts on the space of subgroups. It's very interesting. What are the fixed points? You see, I immediately asked some geometric question. What are the fixed points by conjugation? Somebody said some right answer, I don't know who it was.
Deepak.
Huh? Deepak. So it says, a fixed point says G, H, G inverse equals H. So these are the normal subgroups. So it's a very interesting thing. You look at the set of subgroups, you look at the action by conjugation on this thing. The first thing anybody looks at in life is the fixed points. They're the interesting first things. What are the invariant points? The invariant points by the conjugation actions are the normal subgroups. And we have seen how important they are in our various discussions. So let's say that the fixed points of the G action on, I think I write it, the fix of G on the subgroups of G equal the normal subgroup. And we use this notation. It's very interesting. So the action on G on subs, it's fascinating, isn't it? The normal sub, and conjugation is playing a role. Now look at this thing here. I call it star. Let's look at star. If you're a good mathematician, and you're starting to be good mathematicians, you should formulate this a little bit abstractly. Okay? Not, this is too complicated. Right? If you're, physicists are more intelligent than we are. They can look at complicated stuff and handle it. I can't do it. I have to make a simple something that I can understand. Right? Some big technical stuff physicists usually handles that I can't. So it says conjugation by G of X times the conjugation by G of X times Y, that's the right hand side up there, equals the conjugation of X times the conjugation of Y. That's all right, it's too complicated. Let's define conjugation by G as sigma. Right? It's a mapping. I know it's conjugated by G, but so what does this say? This says sigma of X times Y equals sigma of X times sigma of Y. Oh, does that look good? Right? That looks wonderful. Yes? That says conjugation preserves the algebraic structure in a very strong way. Sigma of X times Y is equal to sigma of X times sigma of Y. It's wonderful. Right? So we say here that sigma is an automorphism of the group. So this is a set of automorphisms of the group. Of the group. These are the guys, the mappings of the group that preserve the structure. Sigma of the identity is the identity, sigma of the product is the product, sigma of the inverse is the inverse of sigma, and so on. These are the automorphisms of the group. Isn't that great? That's great. So look at the logic. Look at the logic when you go home and see and think about what you start. You start with a group. You look then at conjugation action on the group. That's an action of symmetries of the group on subgroups of the group. We understand then we get something called conjugation. Conjugation is an element of the automorphism group, and I just say that this is automorphism group. So this is the I say this is a group of automorphisms. This is a set of automorphisms, but you will check that this is a group. You multiply two automorphisms, you get an automorphism. So this is an automorphism group. So it is completely obvious you should study the automorphism group of a group, because conjugation is an example of such, and you might even guess that almost all automorphisms really are somehow conjugations. This would be a hope. So after all of this, within a very short time, we say to ourselves, we should study the automorphisms of the group. And we have our idea, or a naive idea, only have conjugation. This would be a naive idea. The only thing you have that really twists things around the group are are conjugations. It would be very worthwhile trying to figure that out, right? So you would ask a question, you would have a question, is every automorphism of a group given by conjugation? You should ask this question. This, from the point of view of a professional group theorist, is a categorically stupid question. Because a professional group theorist knows all about this stuff. But nobody in this audience is a professional group theorist. So you're lucky. You have the excuse of asking a stupid question. And if he's a good professional group theorist, he will say, that's a good question for you. Not for him, because he knows the answer. For you. Now the next step, if you're a good mathematician starting out, is to say, what about examples? And you can make this a project for a paper for this course. You understand interesting examples of automorphisms of interesting groups. Okay, let's write down the simplest group we know about. I claim that Professor Malahai in the beginning course certainly talked about this example. Let's call this example Kevon's example. I call it his first name, Kevon's example. Kevon would immediately look at this example if you ask him this question. He would say, what about this thing? We call it Z sometimes, right? You call it Z in this course? The group of integers. Z. Z. So minus 2, minus 1, 0, 1, 2, 3, the group of integers. Okay? Let me emphasize, this is Z with addition. Right? So that's the group structure with addition, right? Okay, you see any automorphisms? You see a map which maps Z to Z and preserves the group structure. Yeah? So we look. See, this is the kind of thing, if you look, you have to go to the bathroom and you're sitting on the toilet, this is picturesque, and you're thinking about this subject, and you're thinking about what are the automorphisms of Z, right? Because you have time to think because nobody's bothering you, yeah? And so you think about, look for automorphisms of Z, sigma, in automorphisms of Z. Right? Well, what is the smartest thing you should do? You should ask, if you have such a guy, where does it take 1? The number 1. Don't you agree that in some sense 1 generates this thing? 1, 2, 3, 4, 5, and so on, and minus 1, 0, and all that. Okay? Okay? What happens if sigma of 1, you start making an experiment in your head, equals 2? You just make an experiment, courageous, right? Then what is sigma of 2? It's 4, you agree? What is sigma of 3? Well, already we're in big trouble. I mean, what is it? 2 plus 2 plus 2 is 6, and so on, right? And so on, and so you say sigma of Z, the whole thing, is the 2, is 2 times Z, right? You get the even numbers. Right? Then if you say sigma, you see you're sitting there, you have nothing to do, you're just thinking about, on the toilet, thinking about something beautiful, and sigma of 1 is equal to 17. I always have 17 as an example, right? And then so you know, you argue a little bit, and that says the sigma of the whole thing is 17 times z. Right? Okay, are there any, then you say, well, you make some really stupid idea, sigma of 1 equals 0. Well, sigma of 2 is also equal to 0. Because 0, yes? Any other ideas what you have in mind? You have any ideas? Sigma of 1 could be, what's missing here? Sigma 1 is 2, 3, 4, that doesn't work. Sigma 0 doesn't work. What else should I try? He's got the right idea. What's your suggestion?
Flip it around.
So sigma of 1 equal minus 1.
Yes.
Okay, sigma, his idea. I'm sorry, I don't know your name yet.
Hannes.
Colin?
Hannes.
Alex. Oh, that's
Hannes. Hannes, like Johannes in the Bible, but without Yo.
You compare yourself to the Bible.
It's difficult, people don't understand.
Okay, so Hannes.
Yes.
Okay, so one of the greatest German mathematicians of the 20th century, perhaps his birth name was Johannes Grauer, and he didn't like that. So he shortened it to Hannes, just like you. Maybe his mother did that, and he didn't like that. So he called himself Hans all the time. Maybe people call you Hans sometimes, right? No, you don't like Hans?
No.
But you should like it because Hans Grauer was one of the most remarkable mathematicians of the 20th century. So maybe you will be the Hans of the 21st century.
Who knows?
Who knows? Yeah, it'd be nice. So here, this is just what you said. Sigma 1 equals minus 1, right? Right? And that's going to be a good one, right? You can check that, of course, sigma of A plus B is minus A minus B, which is equal to minus sigma of A. And you check all the axes, it's an automorphism. Right? So you got it. So ought of the integers is generated by, let's use your notation, the identity. Of course, you always have the identity, right? That's the stupid automorphism, it doesn't do anything. And what he suggested, let's call this guy that does this, let's call this thing, what you call it, a flip.
Yeah.
Let's just call it F for you. I would call it Hans, but you would be embarrassed. So let's call it the flip. So it's a flip, it's generated by the flip. Okay? So it says, and you flip twice, you didn't do anything. So this is the cyclic group of order 2, is the automorphism group of the integers. Very interesting, right? Conjugation is stupid because the group is abelian, right? Conjugation doesn't do anything. So you say, hey, we're very interesting here. Let's go to some big time stuff. Ready? Let's go to the group G, not just the integers. Let's go to the group G of GL2, the invertible matrices in degree 2. Okay? Okay? And in this case, of course, conjugation does a lot. Right? So conjugation by by T is A, T, A inverse. This is non-trivial. This is non-trivial. Conjugation is non-trivial. So here, in the integers, it was trivial, but here it's non-trivial. And you ask yourself, is there any other map you can think of, something like Johannes thought of, this flip, and right, and you had this great idea here, flip of 1 is equal to minus 1, right? So if I would follow Hannes's argument a little bit further, that's the inverse of 1, additive inverse of 1. I might try it. I might try flip of A equals A inverse. Right? Because you thought of some very simple example, which is nice, and then you have some much more complicated thing. But why not try something simple? Yeah? Flip of A is equal to A inverse. So you better start checking if you flip AB, what happens? Because that had here, yeah, you better watch out. So this is A, B, inverse. Right? What's AB inverse? Have you learned that with matrices yet? Huh? What happens?
B inverse A inverse.
Yeah, you know that, right? It doesn't commute. B inverse A inverse. That's equal to the flip of B to the flip of A. Right? You flip it. A times B, and you end up, it goes the wrong way. Right? It's not an automorphism. It's somehow very non-trivial. Then you think about, you see, I hope you're starting to see how I do mathematics. You think about, there's a word here, I hope I didn't erase it. Well, I'll write it again just to dramatize it. It's remedy. You have something here that's wrong, but you maybe can fix it, right? So, the idea is that this guy is anti-commutative, and what I like to do is compose this guy with another anti-commutative thing, and two anti-commutatives make a commutative, something like this. So I look around for another anti-commutative guy, right? I look around for something else that's anti-commutative. And with a little bit of experience, let me call this, I don't know. Let's, I'm going to call it D. I'm going to call it D for dual. D of A is A transpose. Do you know this? You know this idea of transpose? Have you seen it? You know what I mean. Just to make sure, you take a transpose of A, B, C, D. It equals A, and then you put this over here, C, and then B and D. Right? So it stabilizes some things, but it flips something around the diagonal. It's a reflection. Transpose is reflection along the diagonal, right? Isn't that right? Yeah? Now, I'm going to modify on this. Instead of flipping, I'm going to do flip transpose. It sounds like an Olympic diving competition. I'm going to do a flip transpose. And the judges say 7 points for flip transpose and so on, or 82 points. I can't even swim, let alone. I'm so afraid of diving off of a high board. Not afraid, but I just won't do it. Yeah. I learned to swim a little bit recently for exercise, but okay, great. So let's do flip transpose. Let's give it flip hat. Flip hat. Flip hat of A is flip A and then transpose it. Yeah? And you know, of course, that AB transpose is equal to B transpose A transpose also. Right? Right? So, I hope you see we've got something interesting, right? We've got some very interesting automorphism, a very interesting automorphism element of the automorphism group ought GL2 or GLN even R, together with a little project here with Hannes, we have flip hat mapping, which is equal to flip followed by transpose, and if this is and flip hat of A is A inverse transpose, and my friends hate me because I make a simple notation here. My algebraic friends hate me, I write here minus transpose. You don't mind, do you? I mean, I just put them together and say it's okay, right? That's for me, flip hat. Flip inverse transpose. Okay, and you can make a little argument, which would be fun for you to make, that flip hat, so inverse transpose, is not a conjugation. Okay, that's the first thing. It's very interesting, even in 2 by 2, even in dimension 2. It's not a conjugation. Very interesting. Very interesting. Then, after you check that, you should ask the question, is there anything else? So, is the automorphism group of G, it's a fundamental thing, it's the fundamental group, is it not? GLNR. So it is fundamentally important, what is the automorphism group of that? Right? We have discussed conjugations, that's fundamentally important, but now we get in this discussion with Hannes and go around with Fam and these various people, and we see that flip hat, which is inverse transpose, is an interesting one, and the question is, are there any more? Okay? Yes? And then you should write your conjecture. Conjecture, I'll write it. Conjecture, and the German people in the audience know that I like to say this in German, and you need to learn it in German. It's wonderful, 2 words in German. Vermutung is the first one, and there's another word, it's called Mutmaßung. They're more or less equivalent. Are they more or less equivalent? Okay. Are you also German? Yes, Hannes. You're Hannes. Yeah. So they're more or less equivalent words, and let's talk about the word Mutmaßung. Maßung is a way, when you put Maßung on something, I would say it's a way of giving courage. Mut is courage, and Maßung, you've seen these words in German. Mut is courage in this thing. Vermutung is fair. If you put fair in front of everything, it takes it all the way to the end and makes it a big deal. Right? That's Vermutung. And Mutmaßung is a measure, a device to give you courage. In the English word for this, and also the Romance in the Latin language is not, well, German's also language, but in the strongly Roman-based language is conjecture. It's the same in various French and Spanish and so on. So the conjecture is, ready, go? The conjecture is that the automorphism group of GL2R, okay, do it for 2 first. NR is the conjugation group. Let me just write it a conj. Yeah, the conjugation group, semi-direct product, the group of order 2 generated by F hat. It's really a Mutmaßung. I'm really having courage to write this down. Right? First of all, it says that this guy is not a conjugation. It says that this guy normalizes this guy. It says that this is all you get. You can't get anything more. Right? I said, just you think about it if you like, if you find that amusing. Try to prove that fact. Probably you could prove it ad hoc in dimension 2. Or even try dimension 1, I think. No, it's dimension 2. Okay. Let's go to dinner. It's now exactly 6 o'clock. So thank you for your attention today.